This is George Benedetti. Hello.
Hello.
Thank you for taking the time. These are my physics students, and we're asking you some questions. We're going to record this conversation and then disseminate it to, give me a second, the bell. We're going to disseminate our conversation to the American Physics Teacher Association, so literally thousands of high school physics students will appreciate this conversation. We thank you for your time. Maybe you want to begin by just a short explanation of the work, the fine work you've been doing relative to measuring the speed of neutrinos, trying to correlate that to what Einstein had done 100 years or so ago, please.
Now, the first thing to say about the subject is that the experiment turned out to be wrong.
That's fine. That's part of the process, yes?
It's part of the process. It's interesting that it had such a tremendous impact. And the fact, in my opinion, is that the experimentalist people who did the experiment should have been more careful, because this was obviously too much to believe. You see, the theory of relativity is so well tested,
yes,
and is so consistent that although it may be an approximation to something beyond it, in the same sense as the laws of Newton are an approximation,
yes,
to the laws of relativity, although it may be
Will
wrong,
Vitelli, period 2 class, please report to the CAF. Will Vitelli, period 2, please report to the CAF.
I'm sorry, Professor. We're going to stop the announcement. That's the last one you'll hear. Please continue.
Okay. An approximation, this was too much of a violation of the principles of the theory, that particles could travel at speed faster than that of light, was far too much to believe. So it would have been nice if they checked the experiment even more than they actually had done it, particularly because the error turned out to be not a very subtle thing that nobody could conceivably think about, but the simplest thing, that is that connection. And when something doesn't work, like you attempt to light your light on your desktop and it doesn't work, the very first thing you check is that it is plugged in properly.
Yes.
And they didn't do that enough.
So
they turn out to be wrong, probably. This will be checked in a couple of months by having more experiments. We do the same thing, this time more carefully, hopefully. So the field comes out all right from its error, because it's a perfectly normal thing to make errors in research, provided you're able to find them if they are errors. And that's the way it works. Very often we get wrong results, but then when things are redone more carefully, it is proof that they are wrong. And that's okay. That's the way it works. Trial and error, and trial again.
Sure. So, Professor, with that said, in hindsight, had more scrutiny been made relative to the surprise that that something so startling was found? Maybe looking at it a little more closely before announcing it probably would have been more prudent. Is that what I'm hearing?
Yes, definitely.
Okay. All right.
Probably I would say definitely he would have been more prudent. Having the announcement was a little bit like trying to have the cake and eat it too. And this cake was too big to be eaten.
Yes.
So it was a situation that could have been handled with even more care. It was handled quite carefully, but given what happened afterwards, one has the impression that it could have been handled even more carefully.
Sure. I guess you could never be too careful. I guess that's the point. Yes. So just as a quick aside, this is such a celebration today that we have the honor of speaking with you, that following our conversation, we do indeed have a cake in the back of the room that has thank you CERN on it. And were it not so far from Switzerland, we would have you enjoy a piece as well. Maybe another day. So, Professor, with that said, we want to turn it to our precious students. We have questions to ask you. I'll turn it over to them.
Again, the second question, because I will have forgotten. An accelerator is a very simple device in principle. It's an object that accelerates electrically charged particles. For instance, the ones that accelerate here at CERN at the moment are protons, which are the nuclei of hydrogen, and those particles have a charge which is conventionally called +1, just a unit of charge. Now, you have a bunch of these particles traveling, and they come to an object that has a hole in the middle and is charged negatively. So the particle which is charged positively is attracted by this negative plate and gets a little kick. It gets a little bit more energy because it's attracted to the plate. Then it goes through the hole, and things have devised in such a way that as soon as the particles go through the hole, it's always a bunch of protons, it's not just one proton. As soon as they go through the hole, the plate changes what is called its polarity and becomes electrically negative. So now electrically positive. So now it gives it another push because two positive charges repel. So every time the particles go through the hole, they get one kick first, then the polarity changes, the charge changes in the plate, and they get another kick. So every time they go through the hole, they get a couple of kicks, and they gain energy. That's the way we accelerate the particles. It's very simple in principle. Now, the object here that is the most interesting machine at the moment, which is called the Large Hadron Collider, has actually two beams of particles, both of them protons, running in opposite directions in a circular path. And the other essential piece of this object is what keeps the particles going in a circle, one way, or going in a circle in the other way. And that is a magnetic field. There are two tubes, and in each tube there is a magnetic field that deflects the particles inwards. So that's like the rails of a railroad. And the particles going one way and the particles going the other way see two opposite magnetic fields, and that pushes them all inwards in the circle. So you have these two circles, and particles are going one way and the other way. And then it's not quite like a highway. Well, first of all, because it doesn't go anywhere, it's a circle. And second, because it has four crossings, where people driving on the left go to the right, and vice versa. And at those four crossings, the protons collide with the protons, and things happen that allow us to attempt to understand how particles behave at very high energies, and move towards the understanding of the rules of the things that particles are made of, and how those things interact with each other. And these two things, what the objects are that make stuff, and how these objects interact with each other, are the basis of fundamental physics.
Thank you, Professor. Any follow-up questions to that? Taylor? Okay. Taylor, Professor?
I just wanted to know if, since the LHC is the world's most powerful particle collider, are there any risks with the high energy being used?
Is there any risk?
Yeah, because it's such high energy.
No, there are no risks. The reason, well, we forgot the second half of the previous lady's question.
Oh yeah.
But I will come back to that. Definitely I forgot what it was.
Well, it sounds like me every day. Robbie, would you repeat?
Yes. We are both having occasionally senior moments.
I know all about it.
In terms of the experiment, we were wondering how it was possible that they could have measured speed faster than that of light if it can't be exceeded.
Well, you measure the speed, and then it turns out to be whatever it is. And whenever we have measured the speed of something, it has always been smaller than the speed of light or equal to the speed of light. The particles of light have zero mass and they travel at the maximum speed. Particles that have mass travel at the speed that may be very close to the speed of light, but it's always smaller than the speed of light. So the way you measure the speed is you know the distance and you know the time, and divide the distance by the time, and that's the speed. It's simple as that.
We learned that last September, Professor, I thought. All right, good. So, excellent. So,
well, we haven't learned anything beyond that. That's what we do.
Yeah. I need to tell my students while you're here listening, last week I had the pleasure of introducing myself to the professor on the phone, and he said, well, George, what do you do? I said, I teach high school physics students. And he said, well, what age? I said, well, 16, 17, 18. And he says, oh, I wish you luck. So this is it. This is my world, Professor. Next question.
What made the researchers at CERN think to do a second trial after the first?
Sorry, ask it again. I didn't listen. I didn't hear.
John, stand up, please.
What made the researchers at CERN think to do a second trial after the first? And was it the same uncertainty that caused to do a third trial?
Are we going to do a second trial? Yes, this will be done in 1 or 2 months. Neutrinos will be again sent to the laboratory in Gran Sasso that measures the time of arrival. CERN is only responsible for the time of departure. It fires the gun and it says when it did it. And the people at the other end of the experiment in Italy, 732 kilometers away from here, are responsible for the measurement of the distance and the measurement of the time of arrival. Now, yes, we're going to redo the experiment. Since the error has already been found, it's quite clear that the experiment will be consistent with the theory of relativity. But nothing is 100% sure, so we're going to redo it. And this time, not only with one experiment measuring the time of arrival, but a bunch of them, something like 4 or 5, each of them with independent clocks and stuff like that. So the next measurement should be very decisive. And you know, when a samurai makes a big mistake, he, as a demonstration of shame, breaks down his sword after kneeling. If the experiments now still say that the speed of the neutrinos is faster than that of light, I will break my jaw.
No, please. Chalk is expensive, please.
And you can use the pieces, it's
Yes.
With the sword.
It's still
Or a
chalk.
saber.
Indeed. Thank you, Professor. I have a question relative to the clocks you use. So the clocks are measuring a very short period of time. Could you tell us a little bit more about the clocks? How are the clocks constructed to have such precision, such degree of exactness?
Well, there were 2 errors in the experiment that go in opposite directions. One of them was a cable that was not properly connected, as I already told you.
Yes.
And the other one was an American clock.
Professor, with the name Benedetti, it wasn't an Italian clock.